chi-squared test was developed in the early part of the 1900s by Carl Pearson. This stands for chi-squared. This is going to be a sum. So we're going to add up a number of values in a chi-squared test. What does the O stand for? Well, that's going to be the Keon.
Did you do the attendance yet?
Yes, I did. Thank you for asking. Ken, that's kind of rude. But thank you. I will do it later. Now, as I was saying, the O stands for the data you actually collect. And so we call that the observed data. And then the E values are going to be the expected values. And so if you're ever doing an experiment, you can actually figure out your expected values before you start. And then you just simply compare them to your observed values. Let me give you an example.
You know what, Miss Mayfield? I got it from here. Let's say I have an infinite supply of chocolate bars, and I sell to 100 different people. They each take a chocolate bar randomly out of the box. 68 of them grabs caramel. 32 of them grabs almond. Well, is this due to chance or is there another present at work? Also, so the chi-squared test also allows us to answer that. What I'm thinking in my head is called the Null Hypothesis. I said that 100 people would buy chocolate bars, 68 would be caramel, and 32 would be almond. This is the observed value that we get in the experiment. But there's also expected value of it being 50 caramel and 50 almonds. And so you use something called a null hypothesis in this case where you're saying that there's not statistical significance between the observed values and the expected frequency that we get to find what we do actually find.
And chi-squared is cool because we can actually measure our data, or look at our data and see if there's a statistical difference between those two. The best way to get good at chi-squared is to actually do some problems. Before we get to that, there's two terms that must be defined. One is degrees of freedom, and then one is critical values. And so the whole point of chi-squared is to either accept or reject our null hypothesis. And so you have to either exceed or don't exceed your critical value. But first of all, we have to figure out where that number is in this big chart right here.
First thing is something called degrees of freedom. So since we're comparing outcomes, you have to have at least 2 outcomes in your experiment. So in this case, if we have caramels and almonds, we have 2 outcomes that we could get. So we'll say that's 2. And then we simply subtract the number 1 from that to get the degrees of freedom. And so in this case, we have 2 outcomes minus 1, and so we would have 1 degree of freedom. Now you might think to yourself, why isn't there a 0 on the chart? Well, if you just have 1 outcome, you have nothing to compare it to. So that's an easy way to think about that. So we figured out that there's 1 degree of freedom in this case. The next thing you're looking at is for a critical value, and the critical value that we'll always use in this class is the 0.05 value. And so that's going to be on this column right here. So the first thing you do is find the 0.05 value, and you don't worry about all the other numbers. So the 3.841 is something I just know because it means that I'm in the right chart or I'm in the right column.
A way to think of it is being 95% sure that you're either accepting or rejecting your null hypothesis. And you can see that our critical values get higher over here. So you can think as we move this way, if we really want to be sure that we'd have to exceed a higher critical value. So what's our null hypothesis again? Null hypothesis is no statistical difference between observed and expected. And so we either accept or reject that value. So in this case, our critical value would be 3.841. And so when you calculate chi-squared, if you get a number that is higher than 3.841, then you reject that null hypothesis. And so there actually is something aside from just chance that is causing you to get more heads than tails. And if you don't exceed the critical value, you accept that null hypothesis. And this is usually what ends up happening, unless you have a variable that impacts your results. Let's apply this in a couple of different cases.
What y'all nerds up to over here?
The chi-square test? That sounds like a pretty hard test.
It's not a graded test, dummy. It's a test to see if your observed data can be accepted.
Man, I don't understand what y'all talking about. It seems too hard for me. I'm out.
Wait. If y'all could show us some examples, maybe we can actually understand this.
Alright, I'll show you. I asked my Algebra II teacher how much data do you have to get before you can actually apply the chi-square test, and Mrs. Mayfield said that a magic number of 30, and so we want to exceed that number in our experiment. Now what Maggie is going to do is she's going to flip 50 coins. You can see that she's really fast.
The thing goes skrrrrap, pop, 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 pop. Skitty kid pop, pop. And the poop, poop, boom. Skia. Boom, boom. You done know.
So she's flipping 50 coins and then she's sorting them out. And so if we look at that, the first thing, even before we collect the data, is we could look at the expected values. And so we've got heads or tails. And so if you flip 50 coins, how many do we expect to come up as heads? The right answer would be 25. And how many would we expect to come up as tails? 25 as well.
Now let's look at Maggie's data. How many heads and tails did we get? We got 27 heads and 23 tails. Okay, so now we're gonna apply the chi-square test and come up with a critical value. And what does that mean? We're gonna take our equation, which is O minus E squared over E, and we're gonna do that for the heads column. And then we're gonna do it for the tails column. So we also got O minus E squared over E for the tails column. And so our observed value is going to be 27, so it's 27 minus 25 squared over 25. Now this sum means that we're going to add these two values together, so I'm going to put a plus sign right here. Now we're going to do the tails side. So what's our observed value? It's 23 minus 25 squared over 25. Now 27 minus 25 is 2, square that is 4 over 25, plus 23 minus 25 is negative 2 squared over 25, which is 4 over 25. And so our answer is 8 over 25, which would equal to 0.32.
Okay, so that's our chi-squared value for the data that we just collected. Now let's go to our critical values chart. Well, we said that we had 1 degree of freedom because there are 2 outcomes. And 2 minus 1 is 1. So we're going to be looking at the 1, 0 of this chart. And then here's a magical 0.05 column. And so our critical value is 3.841. And so if we get a number higher than that, we reject our null hypothesis. But we didn't. So we got a value that is lower than that, which is 0.32. So that means that we had to accept a null hypothesis. This means that Maggie did a great job at flipping her coins. There's nothing wrong with the coins. There's not way more heads than there should be, and so we had to accept our null hypothesis, that there's no statistical difference between what we observed and what we expected to see. That concludes our explanation for the chi-square test. Thank you for watching.